Hi everyone, my name is Daniel from the Astronomy Data and Computing Services, and this is an introduction to HDF5 with working examples in Python. Throughout this webinar, we will look at some motivation and some background information regarding HDF5, so what is it and why should you use it. We will then cover some core concepts, look at how to work with the file format, and finally look at parallel usage of HDF5 and MPI. So before we start, a disclaimer. I do not intend to cover everything that can be done with HDF5. Instead, I intend to introduce the core concept so that you can continue on your own later. In scientific activity, it's common to have heterogeneous data. For example, it is common for a scientific study in astronomy or astrophysics to use images collected from different telescopes taken at different epochs or location. Plus, different measurements or derived quantities can be obtained from a dataset, like the flux of an object, its redshift, its position on the sky, and so on. For simplicity, you could save all of this data in an ASCII or a CSV file. However, for big datasets, let's say 10 to the 9 lines, the files will get larger due to the encoding. For instance, in an ASCII file, each specific character in your file will take a byte, so 8 bits on disk, and therefore will get very large very quickly. And also it may be slow to access, unless you have some specific mechanisms to access a very specific part of your file. You could also save your data into a FITS table, which is a standard file format for archive in astronomy. However, FITS was never designed for big data. And so if you need to access and write data very quickly in a FITS table, you might have some problems. In practice, if you are using Python, you may want to simplify your life by saving this data into a pickle file or a NumPy zip file. Let's consider the following example. Say you have a 1D spectrum, which here I create using a random NumPy array. To be able to interpret this spectrum, we would need some metadata such as the minimum wavelength value, the delta increment, and the unit. To store all of this together using NumPy, we could save our variables using the saveZ function, and at a later time, load it again into several variables. This method would work for small datasets, but would rapidly become impractical when we have many spectrum or even more metadata to carry forward. We could go around this issue by setting our own arrays or by setting a naming scheme like spectrum 1, 2, 3, and so on. But this would still be impractical for large datasets. So this is where HDF5 comes into play. HDF5 is a mechanism to store large numerical arrays of homogeneous type, data models organized in an hierarchy, and benefit from tagging with metadata. It is designed to handle high data volumes or complex data. HDF5 is an open file format. It is an open source software to work with this format. It is self-descriptive. It can include metadata right next to the data. Its structure looks like a repository path on a file system, and it allows efficient memory usage, can be used in parallel, and therefore can be very fast. Here is an example of a Python program writing an HDF5 file using the package h5py. So as you can see here, we would write our first spectra in a path located at 1/spectrum, where we store our array, and then we can also save some metadata, the attributes here, such as the minimum value, the delta, the unit, and so on. And finally, we could add a second path for the second spectrum, and so on.